As we said, when you combine a metal like sodium with a non-metal like chlorine, the metal is going to be expected to lose an electron and become a positively charged cation, and the non-metal is going to gain an electron and become a negatively charged anion. And the electrostatic attraction between the oppositely charged ions will hold them together in a crystalline structure that looks like this, an ordered arrangement of the positively charged ions surrounded by negatively charged ions. How to write the formula for an ionic compound? These compounds are expected to be electrically neutral, which means they should have an overall zero charge. So the formula has to add up to a zero charge for the whole combination. And we start by writing the positively charged cation first, followed by the negatively charged anion. So if you have a combination of barium with oxygen, barium is in group 2, so it's expected to lose 2 electrons and make a 2 plus cation, while oxygen is in group 6, so it's going to gain 2 electrons and become 2 minus anion. And again, we need to combine these two ions to make a neutral formula. If you put one barium ion plus one oxide ion is going to add up to a neutral combination. So the formula for this combination is going to be barium combined with one oxide. In other combinations, the ratio is not going to be 1-to-1. For example, if you combine magnesium, which is again a group 2 metal that is expected to form a 2 plus cation, with chloride, which is a group 7 non-metal, which is expected to form a 1 minus anion, you can see that in order to make the combination neutral, you will have to add one of these plus 2 of the chlorine to make the combination neutral. So the formula is going to be magnesium chloride with a subscript of 2 that indicates you have 2 chlorine atoms in the combination. In general, in order to have the combination in a neutral ratio, you will actually take the charge of the cation, make it the subscript of the anion and vice versa. And that is going to give you the correct neutral formula for the compound. For this example here, in order to make it neutral, you need to have 3 times 2 plus of magnesium combined with 2 times 3 minus of nitrogen to make the combination neutral. So you will basically write magnesium, take the charge of nitrogen as a subscript for magnesium, and then nitrogen with the charge of magnesium as a subscript for nitrogen. If a polyatomic ion is involved, the number of ions means the number of the whole unit. And this is why we put it in parentheses. For this example here, in order to get a neutral combination, you actually need 2 aluminum, 2 times 3 plus, combined with 3 carbonate, 3 times 2 minus. So when you write the formula, it's going to be aluminum with the number of ions as a subscript combined with carbonate with the number of ions as subscript, but this subscript means the whole unit. This is why we put it in parentheses and we write it outside the parentheses to indicate that it's 3 of the whole unit. This is the formula of ammonium ion, which is 1 plus cation. When you combine it with a chloride ion, You only need one of that positively charged cation combined with one of this negatively charged anion to make the combination neutral. So when you write the formula, it's gonna be NH4 1 for the whole thing combined with one ion of chloride. Sometimes for simplicity, we just ignore the parentheses when it's 1. We write similar compounds like this without parentheses. How we name compounds. The first type is simple ionic compounds. Put the name with the name of the cation first, followed by the name of the anion with adding IDE to the element name. The first example here, we start with the name of the cation, Ba, from the periodic table is the name of barium. And the anion is chlorine, so it's instead of the full name, we'll have IDE at the end. So it's barium chloride. The second example, the name of the cation, K, is potassium, and the name of the anion is oxygen oxide. Third example is magnesium, and this anion is called hydroxide. And this table here gives you the common names of the most common ions of different nonmetals. As you can see, it's the root of the name comes from the name of the element with IDE added at the end. The second type of ionic compounds will involve transition metals rather than simple metals. And the difference in this case is that transition metals are known to have more than one possibility in terms of charge. If we have a combination of iron as a transition metal with chlorine as a nonmetal, we will have two possibilities for iron. Iron can form an iron 2 plus cation or an iron 3 plus cation. Chlorine is a simple nonmetal that will form only one form of an anion, which is Cl minus in both cases. You will need 2 chlorides in the first case and 3 chlorides in the second case, which is going to give you a formula of FeCl2 in the first case and FeCl3 in the second case. And to indicate this difference in the name, we will name the compound following the same procedure, which is the cation name first, and then the anion name in both cases. However, we will use numeric values in parentheses to indicate the charge of the cation because we have two different cases. So we will have a 2 to indicate that it's iron 2, and we will have 3 in parentheses in the second case to indicate that it's iron 3. One more example, if you combine chromium with sulfur, and let's assume that we are dealing with chromium 3 plus, it's possible that chromium would form other ions, so we want to indicate that it's 3 plus in the formula and in the name. So it's going to get combined with sulfur, which has only one possibility as an ion to be 2 minus. So in order to hold neutrality, you need 2 of the chromium ion combined with 3 of the sulfur ions, which means Cr2S3, and the name is going to be chromium with 3 in parentheses to indicate that it's chromium 3 and then sulfide. A special category of compounds is called acids, and acids are any substance that would produce hydrogen ions when they dissolve in water. HCl as a compound is a gas. When you dissolve it in water, is going to actually dissociate and produce hydrogen ions in water, and that's why it becomes an acid. And that's the same case for all halogens. Compounds with all halogens with hydrogen will behave in the same way. And in this case, naming all these acids will follow the same rules, which is hydro and then the halogen name. So for chlorine, it's going to be hydrochloric. For bromine or HBr is going to be hydrobromic. For HF, it's hydrofluoric. For HI, it's hydroiodic. The second type of acids is called oxoacids, and these are acids formed from hydrogen attached to oxygen with a nonmetal. So the name of these acids will be derived from the root of the element name with IC at the end. So for nitrogen, it's going to be nitric acid. For carbon, it's going to be carbonic acid. For chlorine, it's going to be chloric acid. For sulfur, it's going to be sulfuric acid. And for phosphorus, it's going to be phosphoric acid. So as you can see, the root of the element name followed by IC at the end. These are the 5 reference oxoacids that you actually need to memorize with the formula and the name, because it's going to help driving names of other forms of the same oxoacid. You start from the reference acid here, which, as we said, will have an IC at the end of the name. If the formula contains 1 oxygen more than the reference acid, the name will have a prefix of PER, per, and it's going to be a completely different species. If the formula has 1 oxygen less, it's going to end in OUS instead of IC. And if the formula has 2 oxygens less, it's going to have a prefix of hypo. And then when you need to drive the corresponding oxoanion from these acids, it's going to follow the same procedure. The oxoanion derived from the reference acid will have ATE at the end of the name instead of IC. If it has 1 oxygen more, it will have per as a prefix. If it has 1 oxygen less, it's going to have ITE at the end instead of ATE. And if it has 2 oxygen less, it's going to have hypo as a prefix to the name. Let's go over this example here. When you start from nonmetal like chlorine, if you make the monoatomic ion of that nonmetal, the name is going to be the root plus IDE. So it's going to be chloride. If it's the reference polyoxo acid, it should be HClO3, which has the name of chloric with IC at the end. And the corresponding oxoanion should have ATE at the end, which means the ion is going to be chlorate. 1 oxygen less, the acid is HClO2 instead of 3, and it's going to be called chloros. And the corresponding oxoanion is going to have ITA at the end. So it's chlorite. 2 oxygens less, the acid is going to be HClO, which will have a prefix of hypochloros, and the corresponding anion is going to be hypochlorite. And then if it has 1 oxygen more, the acid is going to be HClO4. 4 is 1 oxygen more in comparison to the reference chloric acid, so it's going to have a prefix of perchloric, and the corresponding anion is going to be perchlorate. So let's apply these rules to naming these compounds here. So the first compound is the simple compound, type 1 ionic compound, which is composed of a cation of aluminum. And as we said, we start the name of the compound with the name of the cation, so it's aluminum, followed by the name of the anion with IDE at the end, so it's chloride. We start the name with the name of the cation, so it's calcium, followed by the anion, which is carbonate. That example here is a type 2 example because copper is a transition metal. If you look at the periodic table, you will find it in the middle of the periodic table. So it's a transition metal, and it has more than one possibility in terms of charge. So if you look at the neutrality of that formula, sulfite is 2-, which makes the copper have to be 2+, and we have to indicate this fact in the name. So the name is going to start with the cation name, which is copper, and then we have to indicate the charge using Roman numerals in parentheses, followed by the name of the anion, which is sulfite, and it ends with ITE because this is 1 oxygen less than the reference sulfate with 4 oxygen. It's a type 1 compound, so because sodium has only 1 possible charge, so we start with the name of the cation, sodium, and then the name of the anion, in this case is phosphite, and it's ITE because again it's 1 oxygen less than the reference phosphate with 4 oxygen. And we can go the other way around, which is translate names into formula based on the name. So silver, if you go to the periodic table, you will see that the symbol for silver is Ag, and then sulfate. Sulfate is the polyoxo anion from sulfuric acid, which is SO4. Ag has a charge of +1 based on the location in the periodic table, and sulfate has a typical charge of 2-. So in order to hold neutrality, you will have to have 2 of these in the formula. So the formula is going to be Ag2SO4. Ammonium is a polyatomic ion that we know the formula of to be NH4+, with sulfide, which is the ion of sulfur, S2-. To make this combination neutral, we need 2 of this. To make it 2+ combined with 2-. So the charge 2 here is for the whole thing, which means when you write the formula, it's NH4/2 to indicate 2 of the ammonium ion combined with 1 of the sulfide ion. Nickel 2 cyanide. Nickel has the formula of Ni, and it says 2, so it's 2+. Cyanide, a polyatomic anion that has this formula here with -1. To make it neutral, you need 2 of the cyanide. So that will make the formula NiCN, the whole thing by 2. Potassium periodate. Potassium is a group 1 metal that has the symbol K, and it has 1 plus ion. Periodate is the same as perchlorate that we saw in the previous example, and it's gonna be IO4 minus. Since this is 1 plus combined with 1 minus, it's already neutral, so it's gonna be KiO4.